This webinar is presented by RAIC Emerging Practitioners together with RAIC. We hope you found yesterday's sessions on health and egress informative. Please let us know if any of your questions were not answered in session 1, and we will make every effort to follow up with the presenter for the responses. We will also resend the slides with correction made to the item that was incorrect. Today we're going to be covering the building envelope and structural portions of Part 9 of the National Building Code. Also, please visit our website at raicep.ca or look for RAIC's Con Ed bulletins for future events. With our thanks to the RAIC for their support and hard work, I will now turn you over to our first presenter.
She could have said that. Like, why would you have to read that? You're gonna jump right into it. Can't hear anything. Are other people hearing things?
No, we're all reading this. Oh no.
Oh shit, there's no sound. I don't know. I dialed in.
Is that the speaker?
No, that's just a random person watching. It's cool.
Is she presenting? Is she know there's no sound?
Hello, hello. Now I think it was on mine. Hello, hello.
Yes,
Can you hear me? Okay. Perfect. I'm sorry, guys. It was my bad. I got an okay to go, and I'm going to go back and start again. Okay. Now, Kristen, can you hear me? Perfect. Okay, I'm sorry for that. Okay, we're starting again. Hello, everyone. My name is Herman Weissman, and I'm going to talk about the building envelope part on part 9. Today's session is going to be divided in two. The first half is going to be about concepts, what are the elements that we need to control or cover, water, air, vapor, and thermal. And then the second half is where we're going to get into the National Building Code. So first half, as I mentioned, water, air, and vapor and thermal control. The very first one is kind of we have to control rain. We do have some below-grade infiltration that we have to be considered. And we also have a potential water table below the slab that we have to take into consideration. For the roof, we have gravity, we have rainwater that flows, we have snow that sits, and we do need to have a waterproofing membrane. That membrane has to be water resistant and also has to be vapor impermeable. For the wall, we have a different situation. The water does flow, and we have two planes of protection. The first one is the cladding. Some people call it the weather barrier. We're going to have water shedding or snow shedding from there. We're going to have a air cavity in between, and we're going to have a second plane of protection. That is where we get the moisture, where we put the moisture membrane on the sheeting or the wall we have on the back. For this moisture barrier, it has to be water resistant, but it is recommended to be vapor permeable. We're going to talk a little bit about that later on. For the walls below grade, we have to consider hydrostatic pressure. There's water coming from the water table that can reach part of the walls. There's also floodings or excessive rain that might be flowing through the soil and will generate also some hydrostatic pressure. We have to consider that as well. There are two elements that are interesting also I'm taking advantage and explaining because they are important. They are somehow noted on the code as well. We have something called capillary, which is water flowing through porous materials. Usually it goes from high relative humidity to a low relative humidity. That's something that we see on the foundation walls that flow up, and there's some water that you can see at the foundation walls that come up to grade. The other thing that we have to be considered is about frost heave. It is basically the ice lands that grow below grade, and they might generate some pressure and cracks or movement of the assemblies. For that, this is the first step. You do avoid frost heave using gravel as a substrate. So you allow the water to expand and contract without having the assembly compromise. Air control, it's very hard to see or to kind of perceive. In some cases we do feel it with drafts, usually in all houses. In this case, I put an image of a balloon with water, so you can imagine that that's what's happening in a house. That's the air leakage from a house. So how do we know if a house leaks? There's this element or machine called a blower door test. We put a fan in at the door. and we pressurize the house. We close all the windows, and we also close all the penetrations, range hoods, etc. And we turn on the fan. We take some numbers from there, and we can also take advantage of the moment that we're having the blower test, and check with a smoke pen parts of the building that might have leaks. As we have a high pressure inside the building, you can see on the image below to the left, using a smoke pen to check for air leaks. Let me double check if everyone is hearing me. Please, Camille and Kristen, can you give me a final okay? Perfect, thank you. Okay, we're good to go. Sorry. So, how do we units? Let's talk about units a little bit in regards to air leakage. We have it can be measured by flow, which is cubic meters per second. It can also be measured by liters per second, and very common, at least in the commercial area, it's CFMs. We don't use it on NBC. There's another way of saying or explaining how much of air leaks do we have in a building, and that's through the air changes per hour. And that means you have to calculate the volume. You have to calculate the flow and apply it to the volume, and you get how many times the volume of that house that you're measuring will change air or will lose air, and will need to get complementary air as well. The units we use for measuring or for pressurization are pascals, and you're going to see the at 5 pascals, 50 pascals, or 75 pascals usually. So we turn on the fan and we do different measurements at 5, 10, 15. This is a graph that shows the numbers that we're taking from a measurement, and then if you have a line that's kind of working well, so you can use this information to for the characteristic of the air leakage of the building. Just to let you know, as an information, the atmospheric pressure usually is at 5 pascals. And just for your information, this is ACH, air changes per hour. 50 is at 50 pascals. So the number that you see in all houses will get in between 8 to 10. Current building codes average in between 2.5 to 3.5, and we get up to a very stringent standards like passive house that you have to reach 0.6 air changes per hour. Let's talk a little bit about vapor control. So vapor is the moisture content that we have in the air. The way we measure it, it's the amount of kilograms that we have of water that we have in relationship to the amount of kilograms of dry air. And how do we know how much do we have? And this is the number we usually see. Relative humidity, it's 15%, 30, 60, or 90. So I'm going to take a little time to explain the concept of relative humidity. It's not extensively used in Part 9, but it's very important to understand and understand other elements of Part 9, like vapor control and air control. So let's imagine that we have this guy in a room, but the air is a person. So we have air that is sitting in a room and has some vapor, right? So it's has a glass, and in the glass it's the water or the vapor that is contained in that room. So this guy, air, is having this amount of water, which at 21 degrees, it's around 50% of the relative humidity. So what does this mean? There's something a little magic about this glass. This glass will change sizes depending the temperature that it's located in. Okay? So for 21 degrees, we have a glass of this size, which can hold this amount of water. And this is what the air is capable to do or to hold at 21 degrees. As I mentioned before, the glass has like these magic capabilities, and the problem with this glass is when it gets hotter, well, it's not a problem, but when it gets hotter, the glass gets larger. The same way, when it gets colder, the glass gets smaller. So the same glass, when it goes to 5 degrees, to minus 5 degrees, I'm sorry, it gets smaller. So in this case, at minus 5 degrees, the 100% relative humidity is actually less amount or less quantity of water that this guy air can hold. What's the problem with that? This guy air that is in this room at 21 degrees decides to go out for a walk. So it moves from a place that has 21 degrees to a place that has minus 5 degrees. And the amount of water that has this guy on his glass is still the same. It's still this bunch of water that is moving from one side to the other. The big problem is that now this glass gets smaller, so this is where we get condensation. Okay? Again, we have this amount of water at 21 degrees, and when we move this air to minus 5 degrees, we still have the same amount of water, but the glass gets smaller, and we have condensation. So this is a little bit too technical, but I want to spend 2 minutes showing you guys this. This is a psychometric chart. Some of you might have heard about it or seen. It's used by mechanical engineers and also by building scientists. And this chart, what shows is how the conditions of the air can fluctuate. At the bottom we have the degrees. I marked 10 and 21. And then we have also these curves that show the relative humidity. 10% the lower one to up to 100%, which is the edge, the curve edge line on the left. We were talking about this glass that has 50% relative humidity at 21 degrees. And this is the absolute amount of water that this air has. If we move, or if this guy called air goes out and to a lower temperature space or area, the relative humidity will get higher. And this is where the graph shows you when it gets to 100%, this is the temperature that we getting a saturation of water or condensation. So imagine we go to minus 5 degrees and we get more condensation. There is more and more water that the air cannot hold anymore. So where do we see this? This is where we see what I just explained to you very quickly. On the left side, there's a window. This is a coffee shop in Ottawa that I took the picture from. Lot of paper, a lot of cafes coming up. So we have, that's not a leak on the window. That's condensation throughout the day that gets the vapor, the air that it's inside is at 100% relative humidity. So the frame is cold and you get condensation there. On the right, we see a similar situation, but to the outside, it's a vent. I'm pretty sure this is a dryer vent. So we have the hot air from the inside of the house coming out at -10, -15, -20. It condensates and then it freezes right away. So that's how we get this kind of icicle of ice column outside the vent. Okay, so let's talk about relative humidity and health. A good level of relative humidity is in between 30 and 65%. Actually, to feel comfortable, you want to be no more than 50%, but up to 65% is kind of okay. About relative humidity, we all know when we have a very dry air inside the house, we get dry nose and it's very uncomfortable. You also have the components of the house dry. Many of you might have your hardwood floor shrinking. The other problem of the relative humidity, when it goes over 70 or 80% and there is no light, you provide a good environment for mold growth, and also it's getting more uncomfortable. So let's differentiate something that this is something that gets it's usually people get confused about air and vapor, or air leakage and vapor. So the air is like a rabbit. It will find a way to get out of the building through a hole. Usually houses are pressurized with the HVAC system, and so it will find a way and it will get out of the house. Getting out of the house means that that air goes through the assembly as well and goes from a temperature that is higher to lower temperature. And we're going to see some how the building code addresses that. Vapor, on the other hand, is different. Vapor moves through materials as well. Air might not. You might have an airtight house, but or an area in the house that doesn't have a leak, but the vapor has the capacity to go through or flow through materials depending on the characteristics of the materials. In this case, or in both cases, we have a similar problem or situation where there is a transfer or a movement of vapor content in the air, or vapor content without moving air, that comes from a hot place or warm space to a cold space. So just one explanation how the vapor flows. This is an old house that I'm pretty sure was had a gutter or a downspout that was not well, that was really like broken. So now seems to be fixed. But what we see here, it's that there's like white efflorescence of materials, and what it shows is that now that the downspout is fixed, the water that was absorbed by the brick, by capillary or by just by penetrations, maybe there were holes there, started to dry out back again through vapor diffusion. That vapor diffusion generates, so the water is out, but then there's some residues of the water that was coming in. So that's the white thing that we see on the bricks. So this shows like a process of vapor diffusion, how the vapor works. So this is what the code calls vapor permeance. Vapor pressure goes from higher temperature to So vapor pressure is higher. When the higher the temperature, there's higher vapor pressure, and it usually goes the same way from higher temperature to lower temperatures. The way we measure the vapor permeance is as nanograms per over pascals seconds meter square, and it does depends. It does has a directly relationship with the thickness of the material. Just as an example, we do have open cell and closed cell spray foam. If we use open cell at 1 inch, we have 1200 nanograms over pascal seconds meter square. If you go to a lower information, we have the closed cell where it actually has much less permeance, up to 50 nanograms pascals seconds square meter. So very first question, what's considered as a vapor barrier for what does the NBC consider as a vapor barrier? So we're going to see later on when we read the NBC that actually the closed cell, 1 inch of closed cell is what can be considered as a vapor barrier. Sorry guys, take some water. So let's go to the dew point. Let's explain a little bit. The dew point is what I just spoke about. It's the point in the assembly where the air reaches saturation. So dew point in an assembly will be the place where we have to be careful and we have to avoid having, so if there's some leakage or vapor diffusion, we don't have condensation. So you have an assembly, and there are many ways you can check whether an assembly will have condensation or not. There's software called Woofy that you can place the assembly, and it will tells you what's the relative humidity on each part of the assembly, and you can have a very complicated analysis. You can do then a graph and see where there are potential issues or where areas that we may have some condensation, but we don't have to worry about that now. The National Building Code provides a simplified rules to keep the assembly as safe, safe. There's a good use of a dew point, and that's a dehumidifier. Just as an information for you guys, dehumidifier forces the condensation of water through getting to the right spot on the dew point. The bad consequences of dew point is that if we have vapor diffusion or air leakage and we get some of that air getting into the wall, we are going to get condensation inside of the wall, and we might get decayed or mold growth, which is not good for the building. Let's talk about thermal control. How are we time? We're almost 20 minutes, 25 minutes. Okay, we're good. So for the materials have a property called conductivity. That's not much used, but if you do, conductivity is the property of the material. If you divide it by the thickness, you get the U value, and this is what we are going to use mostly. The overall thermal transmittance or conductance, it's measured as a U value. Metric here is the watts per square meter Kelvin, and imperial it's most what we use in the commercial spectrum. The resistance is the R value, something that I'm sure you guys heard about. The conversion between metric and imperial, you can see there 1 equals to 5.678. usually in the code, we use U values for windows and we use R values for assemblies. They're the same thing. It's just the inverse. Each one is the inverse of the other. Let's talk also about, let's now talk about the nominal R values and the effective R values. We consider nominal R values, and in many jurisdictions in Canada, the building code or the examiners will ask you for a nominal R value of insulation, and that's the thickness of the insulation without considering any of the components interrupting the thermal control layer. Though the effective R value, it's the real resistance of the assembly, and for that, we need to consider all the thermal bridges as well. So let's do an example of this. Let's say we have a wood stud wall. So we have the wood stud that has a certain resistance, and we have the insulation that has another resistance or R value. This is the formula that we have. And there's a way we can calculate the effective R value, and it's through what's called the parallel heat flow portion calculation. So let's do that calculation quickly. The wood stud, it's separated on 16 of center at R 1.25 per inch, and the insulation is at R 4 per inch. So we have 100. The percentage, I already did the calculation. For the wood stud is 9.4, and for the insulation is 90.6. So we place the R values, and we can see that in the parallel portion, the portion that we have the studs, we have an effective R value of 11.61. So this is the value, this is the parallel area. And this is the area that we have continuous insulation. How do we know the effective R value of the entire insulation, the entire wall? We're going to have just to add one RSI and the other RSI. So we have an R value of 11.61 in the parallel portion that we calculated before, and then we have an R4 on the continuous insulation. So the effective R value of this assembly is 15.61. So the question will be, what's the nominal? I would like to ask, what's the nominal R value for the assembly? And here we have the nominal value is R14 plus R4, so we get an R18, but the effective R value is 15.61. So we do have in the code, there is on the notes, in the Part 9 attribution tables, there are notes where you can find, it's 9/593. You have these calculations, and you can also find these calculations through the website of NRCan. And you can also find R values for different assemblies, effective R values, and also nominal R values. In the website, I just took one from the NRCan, and you can have the nominal R value, and depending on the assembly that you have, it gives you right away the effective R value of a typical assembly. Please use that website, and also you can have similar tables on the notes of the NBC. So I forgot to put it on the slides, but it's on 9613. It's in table 9.36.2.61. Okay, so just for your information, the calculation that you see there, it can only be used when you have repetitive components. When you have a more complicated assembly, you cannot apply that formula. And what you need to use is a program. You can have Termflix, so there are other programs where you do that weird assembly, and it will give you the effective R value of the assembly. Okay, so we're good. It's been 35 minutes, I think. So I was counting for 40 minutes. This is the first half, the first introduction. I'm going to, I see that you guys have a few questions there, but let's keep them for later on. Let's try to cover the NBC part. Let's take a 5 minutes break. So it's 12:42. Let's 7 minutes break. So let's come back at 12:50, and we'll go to the second half of the building envelope. Okay, thank you.
Want coffee? He's gone for 7 minutes. I think it's easier than he makes it sound. Like, I remember learning
Oh,
before.
you know what I'm saying?
Yeah, this is a different one. Like, all it is just that you have the thickness of the thing, and there should be an R value chart. You just look it up, and then, like, literally, it's just like 3.5 inches of that gives you that, and then you add. Like, I don't think it's like as complicated as it makes it sound.
I would think that the point of having the tables is so you don't have to do the calculation.
No, but it is just like, if you know what fiberglass is, then you know what the R value of that is. You just times it, and that gives you the R value. And I'm assuming this provided somewhere, because we can't know all the R values probably too.
There's this,
What page is that on?
these are like 39 inches. What's the difference between R value and RSI?
It's the same thing. One's just resistance rating.
Are you sure?
You sure?
Here, final resistance value, common building materials.
Which page is that on?
9597.
Can you read it with the points? I always grab the point.
Look at reading page
Oh,
but I don't see different types of materials. That's what I hear this.
does it give you an R value? Like, clearly states what's the R value?
So did he say like per millimeter? Okay. For example, for thickness of material, it's 100 millimeters. Thermal resistance, it's that. And then this is basically this divided by that, which was his calculation, right? Multiply. Or multiply. Yeah, because this is like, so it says here, thermal resistance per millimeter. Right. Per millimeter. And it's 100, so then you just move the decimal point to. Right, you're right. Same, which is that. This is thermal resistance by thickness less width inch. Okay. So if you had like, 50 millimeters, which I guess you wouldn't have with brick, but let's say you did,
Copy and paste it.
you could multiply 50 by this.
Sorry, I'm wrong. R value is an imperial measurement, RSI is a metric. I think it's the same thing. It's just imperial for symmetry.
Here it's all metric.
So that would be the RSI.
Okay, and to recap, RSI is what? It's the thermal. What is it? It's like a factor that tells you how this thermal resistance. So I think it would be like. So it has a higher thermal thickness divided by the conductivity. So that has a higher thermal resistance number. Does that mean that it's like more insulating? So insulation would just have like a really high, so like here, insulation is sort of thing is like 2.11 So to calculate the whole assembly, you multiply or you add it? Multiply. Because the same for how there was this calculation, conductivity divided by thickness equals U value, but then you said U value is the inverse value. So I think if you divide it, you get the U value. Then if you invert it again, you get the R value. So you could just multiply it. The R value.
Does this show any bad insulation or anything?
Yeah. On page 955. Sorry, 9599.
Bad rock insulation oriented marching to a permanent belt. Must it
What does this mean? 89/92.
Can you ask him to do
Is it a
more?
nominal thickness? Like it either comes in 89 or 92?
Can we do more examples? Is it R value? Relations with different. Can we do more examples? Can we do more
Okay.
examples
Hello,
of
hello.
R value calculation for different samples?
Okay, I'm ready. So just as a reminder, we're getting all the questions, and Kristen and Camille are collecting them, and we're going to address them at the end. Okay, and I'm also going to write like a summary for certain things that I might have forgotten to put on the slides, so you guys have it. So second part, this is what we're going to do on the second part. I highlighted parts of the building code on part 9 that I think are related to what we just what I just explained to you guys. I think those are the more relevant parts, and if you understand why in the code are located there when you take the exam, it will be easier for you, and also for your professional practice later on. It's also going to be easier if you understand why some certain things are set this way. I'm sorry, I'm coughing. I'm not great on my throat. Okay, the idea, so what I'm going to do, I'm going to literally read the sections of the code. Things, as you might have already noticed, are reference and circular and back and forth, so the organization is not great, but we're going to be back and forth in the sections that are more important. So I cannot check. Okay, here we are. Very first thing, definitions. This is something we've seen. The code tells you that the term overall thermal transmittance, or U value, shall mean the rate at which heat is transferred through a building assembly. That's the unit, and then for the purpose of this section, also the effective thermal resistance, or RSI, shall mean the inverse of the overall thermal transmittance. So this is something that I explained. It's basically the inverse. One is the inverse to the other, even though U value is used mostly for Windows and RSI is used for assemblies. The properties, and this is where I'm talking about the cross-referencing. We are going to base all of this on, or the main trunk is going to be on the energy efficiency. And I hope we can go through all of them. I do want to leave 15 minutes at the end, or 20 minutes for Q&A. But we're going to be back and forth, and this is where we see that on the energy efficiency, you actually have to comply with 9.25, which is outside of the energy efficiency part. So the properties, location, and installation of thermal insulation, air barrier systems, vapor barriers, and materials with low air or vapor permeance shall also conform to section 9.25. So let's go to that section. Air barrier systems. Required air barrier to air leakage. Wall ceilings and floor assemblies separating conditioned space from unconditioned space or from ground shall be constructed so as to include an air barrier system that will provide a continuous barrier to air leakage from the interior of the building wall, floor, attic, and roof spaces, sufficient to prevent excessive moisture condensation in such spaces during the winter. Because when we have some leaks, we have condensation in the assemblies. And from the exterior, this is something I didn't talk in the first half, or the ground inwards sufficient to, and I'm going to jump directly to number 3, minimize the ingress of soil gas. In this case, we are using the air control layer to protect soil gas from penetrating. In some areas of the country, we have more stringent laws, or our codes are requiring to have elements to actually extract potential gas, radon gas. And then the continuity of the air barrier systems, where the air barrier system consists of an air impermeable panel type material. All joints shall be sealed to prevent air leakage. Okay, so this is why we split on control layers, because some components in the assembly can be used for a couple or 3 roles, or so in this case, if we are using an air barrier system that has a panel type of material that is not a membrane or poly or maybe a paint or a liquid applied membrane, we do have to be sure that it's sealed so all the seams are tight and we prevent air leakage. Calculation of effective thermal resistance of assemblies, and this is where the code does require you to calculate. In calculating the effective thermal resistance of assemblies for the purpose of the comparison with the requirements, blah blah blah, the thermal bridging effect of closely spaced repetitive structural members such as studs and joists, and of ancillary members such as lintels, seals, and plates shall be accounted for. And here's where you see the note that you might be that you can use, and this is the reference within the National Building Code with the calculation that I send you is the same calculation, and you have it on the National Building Code. So we do have to calculate thermal bridges of studs, joists, lintels, seals, and plates. But there's some stuff we don't have to calculate. So I'm going to read it all. Minor penetrations through assemblies such as pipes, ducts, equipment with through-the-wall venting, package terminal, air conditioners, or heat pumps, shelf angles, anchors, and ties, and associated fasteners and minor structural members that must partially or completely penetrate the building envelope to perform their intended function need not to be taken into account in the calculation of the effective thermal resistance of that assembly. The same situation goes for major structural penetration such as balcony and canopy slabs, beams, columns, and ornamentation or appendages that must completely penetrate the building envelope to perform the intended function need not to be taken into account for the calculation of the effective thermal resistance of the penetrated assembly, provided the insulation is installed tight against the outline of the penetration and the sum of the areas of such major structural penetrations is limited to a maximum of 2% of the gross wall area calculated. Okay? So for those things, if we have less than 2%, we don't need to calculate the thermal bridging. I took one table. There are a few tables on the code. I took this table to calculate for the requirements of the minimum effective thermal resistance of above ground opaque assemblies. So as the code is telling you, these are the effective thermal resistances, you need to calculate the effective R values or U values. So how do we read this table? We have different zones depending on the house or the building that you guys are designing. You have to choose or get the zone. This is something I also missed to put. You can get the zone through, let me see. The Appendix B, Division B, Appendix C, you have climatic and seismic information. I'm going to write down and send it to you guys, but you have cities throughout the country, and you can find the degree days below 18 degrees centigrades, and you have a number there. So depending on the area that you go, let's say that we are in Regina, Saskatchewan. So we have degree days below 18 is 5,600. So if we want to get the minimum thermal resistance of the assemblies for Regina, Saskatchewan, we are at 1,500. So we are in zone 7A. So we will get, can you see this? 7A. So we'll have to use this table. Okay? I'm going to take a little one, like 3 minutes, just to talk about, no, I'm sorry, I got confused with the next slide. Energy rating, minimum U values for Windows. The same situation applies for Windows. In this case, Windows are calculated, differently. What you have to take from the Windows, when you buy a window, you have an energy rating, and this is a standardized size with a standard way of measuring it that you get from the Windows manufacturer, and that's a number that you have to use. So in this case, the U value should be no greater than an energy rating, not less than the value listed below. So you have, again, you choose the zone, and the windows that you're specifying for your building should comply with that table. Okay, so I'm going to take a little bit, couple of minutes just to talk about permafrost, and this has to do with it's an interesting and building science and insulation use of building science concept use for insulation. There's a requirement in the code that if you're building in a permafrost area, in an area with permafrost, you have to have a particular designer competent in this field, and here's why you need that. The picture shows a house that is moving, like that is tilted, and that's because when you have the foundations on permafrost and you have heat loss from your house to those foundations, you basically melt or thaw the permafrost. So that's where you lose grip and the house starts sinking. So you have to be careful, and in this case, you do need to insulate the elements that are below grade or the elements that are connecting to the ground. So let's see, for example, this table. So we have here in this table an effective thermal resistance of assemblies below grade or in contact with the ground, in this case without heat recovery ventilator. So here's where I marked. I mark zone 7B and zone 8. And this is where we see that there is a heated and unheated floors on permafrost. When you're in a zone, in zone 4, 5, 6, 7, you basically don't have permafrost, or it seems that you don't have. But when you jump into 7B or 8, that's where you do have to put insulation for sure, because you might have heat losses through that wall, that assembly, and you don't want that to sink. So permafrost, for people who might not know, it's part of the country are in constant below freezing or close to below freezing temperatures, and it's an entire layer of the ground that it's frozen. So it's not soil that has the temperature is usually below zero or at zero. When with climate change or with the change of climates in certain areas of the country, we're having thaw of the permafrost, but that's another topic and not for this presentation. We're with time, very good. Okay, air tightness. The leakage of air into and out of conditioned space shall be controlled by continuous air barrier system. And here's where we start getting a number or an element, and this is where the code requires or asks you to have an air leakage rate no greater than 0.20 liters per second per square meter. So this is where you use a blower door test and where you can check what's your air leakage. And the calculation for that in this case is required to be tested at 75 pascals. So I'm not going to get into that again, but you guys in the first half, it's basically what I show you on the table, and the process should be done with a blower test. And when you use multiple, well, yeah, that's it basically. So that's why we talked about that before. Construction of air barrier details. You do have to seal and tape penetrations to make it continuous. So let's jump to vapor barriers. Require vapor barrier to vapor diffusion. Thermally insulated walls, ceilings, and floor assemblies shall be constructed with a vapor barrier so as to provide a barrier to diffusion of water vapor from the interior into wall spaces, floor spaces, or attic or roof spaces. So this is different as air leakage, and I already pointed that out, and it's a different thing. We have to provide components in the assembly that provides a vapor barrier. So, and here's where we get a number, and this is the number that the code requires you to have as a vapor barrier, that the permeance of the component, which the full thickness of that component in the wall assembly has to be no greater than 60 nanograms over pascals seconds meter square. Okay? So, a little reminder, 1 inch of closed cell spray foam, you get 50. So that layer can be considered as the vapor barrier. So you can use that instead of using poly on the inside. So everything that I explained about vapor barrier is for this line. Not everything, but most of it. And here's where we see the rule of thumb or the easiest way of keeping the assembly healthy and safe. We don't need to do weird and difficult calculations. What the code tells you is that the products installed to function as vapor barriers shall protect the warm side of the wall, ceiling, and floor assemblies. And again, where different products are used as a vapor barrier, for the vapor barrier and the insulation, the vapor barrier shall be installed sufficiently close to the warm side of the insulation. So you can use spray foam insulation as the vapor control, but you can also use another product, a membrane, that will be the vapor control or the vapor barrier, and then you can use mineral wool or another type of insulation. If you're separating the components, the vapor barrier has to be on the warm side of the insulation. Okay? Where the same product is used as the vapor barrier and the insulation, the product shall be installed sufficiently close to the warm side of the assembly. Again, same situation. 1 inch of closed-cell spray foam can be considered as a vapor barrier, but that 1 inch of closed-cell spray foam has to be installed in the warm side or close to the warm side of the assembly. Okay? Position of low permeance materials. So again, the low permeance materials is this closed-cell spray foam, for example, and it has to be installed in the warm phase of the assembly. And this has to do with another thing. You want to prevent vapor coming from the inside to the outside because we are in a heating-dominated climate, most of our country or all of our country. And you do want to have, if you have some condensation or some leaks within the wall, you want those leaks or that condensation to dry outside in the summer. So this is where the code tells you put the low permeance materials inside in the warm side and and this is the building science part, not the code, leave the high permeance or more the components that have good vapor diffusion to the outside. And this is why I show you the image of the brick that dried out. The brick, in that case, not that they thought much about it, but has a high vapor permeance, and so all the water that we have from the gutter, when they fixed the gutter, the brick was able to dry out and maintain a low amount of moisture inside the assembly. Okay, so we're at 110, we're good. So I have almost 20 more slides that we can go. I was a little concerned that we were not going to be able to get to the extra slides, but we have plenty of time. So these are things that I separated on different control layers. So weather barriers, first and second planes of protections. That's something I show you guys at the very beginning. Where walls are required to provide protection from precipitation comprise cladding assemblies with first and second planes of protection. The first plane of protection shall consist of cladding, very simple. The second plane of protection, I jump directly to B, shall be designed and constructed to intercept the rain and snow and effectively dissipate any rain or snow to the exterior. So that's basically telling us not only you have to have a membrane on the second plane of protection, but you also have to dissipate that water or rain that can penetrate, and the way you do it is through flushing. At the bottom of each wall, we do have to have a flushing that will dissipate that water that might come in to the outside. Waterproofing. Where hydrostatic pressure occurs, Waterproofing is required for assemblies separating interior space from the ground to prevent the ingress of water into building assemblies and interior spaces. So this is what I show you at the very beginning as well. When we have water table higher up or at the level of our footings or footing walls, some areas we do have the water tables pretty high, or in areas that we want to prevent flooding to get into the house or excessive rainwater in that particular plot or lot. We want to have waterproofing. Also, we do need waterproofing for underground structures. So in the case that we have some green roof or a structure that is below grade that has a roof, we certainly have to have a good waterproofing there. It's not just about waterproofing. Waterproofing will prevent water to come into. The best and the more expensive you get, it's the more resistance, but you also have a way of decompressing the hydrostatic pressure, and that's by draining the below grade assemblies. In this case, the code is asking or telling you, unless it can be shown that to be unnecessary, the bottom of every exterior foundation shall be drained by drainage tile or pipe laid around the exterior of the foundation. It's also telling, or by a layer of gravel or crushed rock, which is also very good for what I told you about frost heave. Okay. We can also, and that's something that I'm adding up, the code here says, or talks about mineral fiber insulation or crush rock backfill to be adjacent to the exterior wall foundation. It's kind of difficult to really build a crushed rock. I mean, it has to be a lot if you have, but you can do it, or mineral fiber. It's also, this is for you guys to just to know, dimple board is what you can use as well, which is a layer that has some airspace and it has to be extended to the footing level. What it allows you, it facilitates, this is what the code tells you, and this is what happens, facilitates the drainage of groundwater to the foundation drainage system. So any water that you have that is pushing the envelope or pushing the wall, the hydrostatic pressure will be decompressed and drained down to the drainage system. So we have a minimum size that is asking or telling you the code to do minimum of 4 inches, 100 millimeters diameter. The installation, there's something important here that is telling us the ground material shall be laid on undisturbed or compact soil to a minimum depth of not less than 125 millimeters beneath the footing of the building. And that's because you want all the water to dry out of the footing of that building. And it has to extend also 300 millimeters beyond to the side. What you want is to guarantee that that area with granular material will properly drain any water that might come up. And grading seems to be logic or kind of unnecessary to explain, but it is important to be explicit and to grade the interior area. Sorry about the phone. I'm going to turn this off. Sorry for this. Okay, I'm back. The National Building Code allows you or tells you that the drainage disposal of the foundation drains shall be drained to sewer, drainage, ditch, or dry well. I would like to point out that many jurisdictions in the country are not allowing anymore to drain to the sewer or not even to a drainage, municipality drainage. Some areas are actually requiring you to drain to your own backyard, or to, yeah, that's basically just my comment. Some pits where gravity drainage is not practical, an automatic sump pump shall be provided to discharge the water from the sump pit described in sentence 1 into a sewer, drainage ditch, or dry well. A sump pump or a sump pit, it's basically a bucket that you put on your basement, and that is connected to that gravel or the drainage tile. And when you have excessive water, that bucket will be filled, and you'll have an automatic sump pump that will activate and will throw the water to the outside or to the sewer or to a drainage ditch or to a dry well that you might have in your property. And what is a dry well? You need to guarantee that there's no groundwater level that is going to get to that dry well, so you have to be sure that there's no water table coming up. And certainly that drainage has to be away from the building, because you're draining that water and you don't want to have any compromise on the building structure. Drainage, control of water ingress. Again, grading and drainage. It is talking about hydrostatic pressure. And this is something I already talked, where groundwater level may cause hydrostatic pressure beneath the floor or ground. The floor and ground shall be a poor concrete slab and designed to resist such pressures. So it is important. The way also you can avoid potential damages is to add a gravel and drainage board on the walls, and have gravel underneath on the slabs, underneath the slabs. Control of rainwater penetration, except for masonry veneer. So it's telling you that if you're using a cladding, it has to be 75 millimeters thick minimum. And it's also telling us that the veneer described over wood frame walls should have no less than 25 millimeters of airspace behind the veneer. And this is the air cavity. We need to have 25 millimeters of space. And then we have to have the second plane of water control. Flashing. What is flashing? Flashing is the element that we use. It's to deflect the water to the outside. So the flashing has to be beneath the weep holes. So again, what are the weep holes? The weep holes are when you have a brick veneer, you do have to put weep holes at the bottom and at the top as well, so you have that ventilation, the cavity that you have in between the brick and the wall has to be vented, and any water that might ingress to that cavity has to be flushed out with the flashing. Let me show you one picture. This is a building that has no flushing to the outside, so the water just sink in. And what we're seeing here is it's going through the column, but anyway, this is a wrong solution for building assembly. The other thing is that the flashing has to be watertight. It's not just about putting some metal that is overlapped, but also has to be watertight. And here's what I just talked about, the required weep holes. Weep holes spaced no more than 800 millimeters apart shall be provided at the bottom of cavities in cavity walls, in cavities or air spaces in masonry veneer walls. The weep hole, or the upper hole that I was talking about, has to do with allowing ventilation in the cavity as well. Protection from decay. In this case, for wood frame construction, ends of woods of wood joists, beams, and other members framing into masonry or concrete shall be treated to prevent decay from the bottom of the member as member is at or below ground level, or a 12 millimeter airspace shall be provided at the end of the sides of the members. What it's telling you, the code here, is that if you have a wood member, you actually want to leave a little bit of a space and not touch directly to the side. So if you have some water getting into the assembly, will not touch directly. And the second point, airspaces required shall not be blocked by insulation, vapor barriers, or airtight materials, because you want that water that might come up to dry out. So you don't want those things to connect or being touching one to the other. Protection from dampness, except as for instance, two wood framing members that are not pressure treated with wood preservative and that are not supported on concrete in contact, and that are supported on concrete in contact with the ground or field shall be separated from concrete by no less than a 0.05 millimeter polyethylene film. And this is what I talked at the very, very beginning about capillary. So if you have a concrete base and you have a column or a beam, a wood column or a wood beam touching directly into that, you might have some water flowing through the pores of that concrete, and they will penetrate into the wood, will rot, and will decay. So you do need to separate those two components with a polyethylene film. How are we with time? 1:23. Okay, I think we're going to be good. Heat loss control. So this is not part of the. So these are the minimum values that you need to comply. This is a different way that the code is providing you an option to use, and you can have the design temperature. You can use the design temperature, and that's the minimum U values that you can use, that you have to use on the windows. Depth of foundation. So there is a minimum depth foundation when, depending on the type of soil that you have, the foundations have to have a minimum depth foundation. And in the case, for example, of clay or soils that are not clearly defined, you need 1.2 meters. And this is to avoid, has to be below the frost line. Vapor control. Except where it can be shown to be unnecessary, where insulation is installed between a ceiling and the underside roof sheeting, a space shall be provided between the insulation and the sheeting, and vents shall be installed to permit the transfer of moisture from the space to the exterior. So this is the vented roof. The vented roof, it's a roof that is protecting from the weather. The sheeting has a membrane on top, and you do need to have some air space in between that sheeting and the insulation with venting. So any moisture that comes into that area will be able to dry out. There are some minimum clearances for that vented roof. Ceiling insulation number 3 shall be installed in a manner that will not restrict the free flow of air through roof vents or through any portion of the attic or roof space. So basically what it's saying is that you can do whatever you want, but you have to maintain the flow of air, so any moisture that gets into the vented roof can dry out. And this is the last slide, and then we can jump into questions. Protection from soil gas ingress. It's already noted on the energy efficiency part. But all wall, roof, and floor assemblies separating conditioned space from the ground shall be protected by an air barrier system. We discussed this lengthily. And this is where the code is requiring you to have for a depressurization system. So floors and ground shall be provided with a rough-in for subfloor depressurization consisting of gas permeable layer, an inlet, and an outlet as described in sentence 2, blah, 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 clean ground raw material. Basically, what it's telling you is that you have to provide the possibility of depressurize the subfloor. So if you have some radon or gas that are in there, so you can extract those gases to the outside. Okay, so I'm done with all the hard elements, with all the main components of part 9 for building envelope. I'm going to check in with Kristen, but I think I can start answering some questions. The questions that I might not know or I might not be sure, I will send back you guys a list answering them. So, Kristen. Okay. So I'm going to start. I have a list of questions here. Let me. Start with the very beginning. So will you have such calculation? Oh, okay. So I think this is the percentage, where the percentage came from. Okay, so I think we're talking about slide 25, which is the wall assemblies. The percentages that you guys can find on the effective value or the let me go to that slide. So I guess this question is where do we get this percentage and this percentage? So this percentage is this part of the assembly, so it's 9.4, and from here to here you have 90.6. So as the assembly is repetitive, you have throughout all the assembly you have 9.4% DR value of the wood, and you have 90.6% DR value of the insulation. That's a calculation I did. So if the wood is 1.5 inches and the rest it's let me think out loud. So we are at 16 of center, so we have 16 inches minus 1.5 inches. So we have 14.5 inches and then 1.5 inches, so that's the percentage. On 100%, 14.5 is 90.6. Where can we find the R values in the code table? It was responded.
Well, I don't understand. So you're supposed to get 100%.
So I can send you guys the part of the R values, but it's on the. You should read on the division V. Part 9 attribution tables. There is a notes to part 9. In the middle of the notes, you get examples of calculations. You have R values, you have effective R values, and nominal R values. You have percentages of framing area and cavity area as well. It's basically one next to the other. From, if you see the page at the bottom, 9553 to
that much is 9.4, that much is 9.6.
You have the
It's
R
repetitive.
values on thicknesses of the materials up to 9603. Sorry, 9604.
I'm not sure what this is.
Can you repeat the
It's just
table?
what's that in installation?
Okay,
Like
I
gypsum
just-
and like.
I'm going to send you the list of the tables and updated slides. 30% from the slide I discussed.
Oh, you mean that's orange?
The link on the NRCan, I'm going to review it, but you can also check, it's on the NRCan website, effective R values, and you're going to find it right away. That's another option, but I'm going to update the links to that.
No, yeah, because you pointed to the arrow earlier. I just don't get where you're orange and like.
Okay, I'm reading the questions. Can we please go through the example on page 9593? Okay. Fine. 593.
Oh, this is RSI.
So I should repeat the questions, right? So there. Can we please go through the example on page 9593? See the example of this. Yes. So let's go. The example on page 5953 is this. It's very similar as the example that I'm showing you here. So it's saying that the area of framing is actually 23%, and the area of the cavity is 77. So instead of having here 9.4, here is having 23%, and here is having 77%. Okay, the formula, I'm pretty sure is the same. Yeah, the formula is the same. The RSI parallel, it's exactly the same formula. So it has to do on the distance in between the wood studs. Okay.
So that has to do with distances, your structural numbers. That's why you calculate that.
Can we do more examples with R value calculations with different assemblies? I don't think we have time to do that. Let me go through the other ones, and I can provide you with like a couple of options afterwards. But yeah, I don't think we're going to do that now. Can the vapor barrier use as an air barrier or vice versa? Yes. Yes. So, the vapor barrier, as a rule of thumb, has to be on the warm side. So whatever you use as a vapor barrier has to be on the warm side. You can use a poly, you can use OSB, you can use plywood. In the case of panels, has to be taped. You can also use rigid form insulation, and you have to tape it. But that piece of vapor barrier that has to be below 60 nanograms, blah, 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 has to be on the warm side. That can be used as an air control layer as well. If it's properly taped, that can be used as an air control layer as well. But let's, for example, think that your client or your design is not using a vapor impermeable insulation material. It's using mineral wool, or it's using cellulose insulation, or it's using fiber, blown fiberglass, or maybe a fiber bat. That's vapor permeable. So you cannot. So you cannot use it as a vapor barrier. Let's say the question is different though, and I'm getting out of the line. Vapor barrier and air barrier. Let's say because of constructability, in many cases the air barrier is better to be used on the outside, so you avoid all the joists on the inside. So you decide for X reason that you want the vapor barrier, the air barrier to be on the outside, so you can be very continuous and not have any joist on the interior to intercept them. So you can have the air barrier, let's say, on the sheeting, and have instead of using a regular Tyvek, you might want to use a peel and stick membrane that you guarantee that will maintain the air tightness. But in this case, the air control layer will be on the cold side. So you do need to use another component as a vapor barrier that has to be on the warm side. So in some cases you can use it, and in some cases you need to have it separately. The air control layer or the air barrier can be either on the warm side or on the cold side, where the vapor control layer or the vapor barrier has to be only on the warm side. Slide 42. Can you give an example on slide 42? Let's see.
Sorry, Emma.
Okay, I think I just gave an example on continuous air barrier. I could. I'm going to send you a picture of a couple of projects we work on, showing the air barrier to be on the outside and the vapor barrier to be on the inside. Location of zone tables. Revised location of zone tables, slide 45 and 46. Might have been my mistakes. Not sure what it's talking about, but location of zone table is actually, I'm going to tell you where it is. It's on Appendix C. So I'm going to write this down. Sorry. Okay, guys, I'm going through like the old questions, and then I'm going to. Okay, I'm a little overwhelmed by the amount of questions. So let's continue with the older questions, and anything that we will not have time today, I will address them in another page. Okay, so location of the zone table. I'm back. Again, it's on Division B, Appendix C. It starts on C. Starts on C11, and you have different provinces. There's a column called degree days below 18 degrees centigrades. That's the number that you have to compare. Okay?
Division B, Appendix.
These OSB taped seams permitted by code for use as a vapor barrier. It is, and I'll explain you why. That's a great question. What you have to do, OSB, depending on the thickness, for a vapor barrier, you have to have material that has a permeance below 60 nanograms and all that number. The OSB in particular, and this is something it happened in our firm, if you have 11 millimeters of OSB, you're actually over 60. So for the building code to consider that as a vapor barrier, you have to use minimum 3/4 of OSB, and that's where you get the below 60 nanograms. So it can be used, but you have to show in the specs that the thickness that you're using as a vapor barrier will have a vapor permeance below not greater than 60 nanograms. So it will be below 60 nanograms. So yes, you can use it. Has to be, yeah. And if you tape it, it's also be considered an air barrier. Determine when to use damp proofing and waterproofing. So You can use a dam proofing below grade when you show that there is no water table close or near to the footings of the foundation. It is certainly cheaper and easier to do a dam proofing only, but if there is a water table nearby or hydrostatic pressure that might be happening in the wall assembly, you need to use a waterproofing. What is the minimum slope for flashing? I don't really know. I don't think the code tells you. It has to be sloped. Doesn't really. That's a question. I never encountered it, but I don't think it tells you the code. But for has to be, I guess, 2% minimum. I don't know. I will double check and get back to you guys if there is something in the code specifically on that. Cathedral ceilings with SPF insulation between roof, purlins, need ventilation from roof cavity. The code will not tell you specifically for that. What you have to say, or what you have to do, is to show that there is no vapor. There is a vapor. I'm going to answer that question a little more extensively with when I send you guys back the things, because it's not that easy to explain. The code doesn't tell you specifically about the SPF insulation. What you have to do is you have to comply with other things. So I'm going to jump into the next one. What is type S roll roofing? I will double check that. I don't really know. Is exterior spray insulation problematic because it is on the warm side of the building? Because it's not. So one question is it exterior spray insulation problematic because it is not on the warm side of the building? Somehow it is. I guess you're talking about closed cell spray foam. So the closed cell spray foam doesn't have permeability, so any moisture that you might get in between that exterior closed cell spray foam and the interior vapor barrier will not be able to dry out. If you fully use spray foam up to the vapor barrier, you're safe. But if you are having exterior insulation and you have other components and then you have the vapor barrier, you're going to generate potential problems. That's mostly building science thing. It's not in the code, but it's interesting to know that. So what does high moisture so table 9.733, what does high moisture generation in sentence 3 means? So I'm not going to even check that on the code, but I'm pretty sure it means that, for example, the picture I show you, a coffee shop that has non-stop boiling water, that's a high moisture generation component or type of occupancy. What is the difference between table 933 and 936.2? So the 9733 is just complying, it's the basic compliance, and the table 9.36.2, it's on the high energy efficiency compliance. So the first one is the minimum requirement, and the second one is for high energy, for energy efficiency. In defining the U values of that's a continuation. Okay, so it's the same thing. So defining the U values for the windows, those tables, one table is the minimum that you are required, and if you want to do a high energy or high efficiency building, you have to go to table 9.36. Can you please explain location of low permeance material again? Yes. So this is where the code gets confused because it's the same thing. Low permeance material is a vapor barrier. Okay? So a vapor barrier is comprised by a low permeance material. the way we control the vapor is having a low permeance material that will stop the vapor flowing from the warm side to the cold side. Cannot find wood stud in those tables. I don't know exactly what's referring, but I'm pretty sure we will be able to find them. I'll check it out. Where the weeping tiles must be used. The weeping tiles have to be used on a brick veneer wall assembly. When you have a brick used as a cladding, you need to put weeping tiles. I'm sorry. No. We're talking about. Sorry, weeping poles. I'm confusing weeping poles with weeping tiles. So weeping tiles must be used. Sorry, that's the weeping tile. It's a duct that you have below grade surrounding the perimeter foundation, and that's something that you put. So what I've been reading that the code requires you only to have gravel, but if you want to move that, if you have excess water or a water table nearby, you actually want to have a weeping tile that will collect that water and will go to the sump pump if necessary. Or in some cases, what you do is you connect that weeping tile to the below grade slab gravel, and that gravel is connected to the sump pump. So in case of a flash flooding or some water table raise, you will be able to extract that excessive amount of water through the weeping tile. Next question. Can you explain again the difference between RSI and U value? Yes. This is a good question because it seems simple, but it is kind of complicated to grapple, to understand. Let me open. Okay. So RSI value and U value account for the same physical action or the same phenomenon, which is the heat transfer from one side of the material to the other side of the material. So we have heat coming from a hotter space to a colder space. The heat will go through. It will balance out. So if you have a mineral wool or an insulation material, you're going to have that material will allow that heat to flow faster or slower. How do we measure that? We measure that with U value or with R value. It's the same thing. It's the flow of heat from the warm side to the cold side. But the U value shows you the transmittance. So it tells you how fast that heat will go from one side to the other. The R value, or RSI value, which is the same in this case, it tells you the resistance. It's like how much can resist that same product, the heat from going to one side to the other side. So the number of the phenomenon is the same. Sorry guys, I need to drink some water. And that's why the R value is the inverse of the U value, and the U value is the inverse of the R value. So it's the same element, but it's just the inverse. One is the resistance. Is how do you measure it? You say, okay, I can resist this amount. And the other one says, well, I can transfer this amount. I hope that explains or that clarifies. It's, I don't know exactly how can I be more clear on that. Is RSI parallel different from RSI? No. So RSI parallel is the calculation you do. So this is the difference. The difference is in between nominal and effective. So the RSI parallel means that is the RSI that you're going to get on the area of the assembly that has parallel heat flow calculation. And then you have an area of the assembly that will have continuous insulation, but they're kind of the same thing. It's just assigned to a different part of the component of the assembly. If you use two vapor barriers, like some app using vapor barrier and in lieu of air barrier, will there be condensation and water build up inside? Yes, I don't think they asked that, but you don't want to use. You're not allowed to use two vapor barriers. You just have one vapor barrier, and the wall usually has to be able to dry to the inwards and outwards. So you have the vapor barrier on the warm side, and anything water that you might get in the gypsum or maybe in a service carrier that you have will be able to dry it inwards. And then from that vapor barrier to the outside, you have to be able to be vapor permeable, so it can dry to the outside in the summer, for example. How is the R value of the stat in parallel effective R value calculation determined? Oh, that's me. You can go. I know that the wood has an R value of 1.25. That's me, and you can find. I'm not extremely sure if the wood value or R value is on the table in here, but yeah, that's the data I get. I usually can get R values from the spec sheets of all materials. How do you identify city versus zone table? How to identify city versus zone table? I'm sure I understand that, but in the zone table you have a province and then you have the different cities. So what is the minimum downturn for flashing? Oh, like I already answered, or I said that I'm not sure, but usually it's 2% minimum for, but you have to show some slope. Can you please explain your comment on slide 50 on 1-inch close spray creates a permeance? In the NBC, it indicates vapor barrier shall have a permeance not greater than 60. If 2 or more inches of spray foam is applied, how does this affect the vapor permeance? This is measured through the overall square footage? Yes, okay, this is a great confusing question. I'm going to show you. So it's a very common confusion. Where's the? Oh, it's not here. What's that? Slide 50. So the vapor barrier has to be lower than 60. So put 60 and put lower than 60. Let's see. Okay. So here we have extreme this spray foam close cell 1 inch. That's something I took it from their specs. I didn't do any calculations. They tell you for 1 inch of elastochem or this close cell spray foam, you get 50 nanograms. So the vapor barrier has to be not greater than 60, so it has to be lower than 60. So in this case, 50 is lower than 60, so it is considered a vapor barrier. If you use 2 inches, you actually go lower, so it's more of a vapor barrier. So you get to 24.6. So it's still a vapor barrier, so it's fine. So you have to have minimum 1 inch. The more you put, the less vapor permeance you have, so the more vapor barrier it is. So the way it affects having more insulation is that you get a better vapor barrier or a more vapor barrier or a less permeable vapor barrier. In contrary, if you use an open cell, let's say you use 1 inch, you have 1200, and this is like very high. It's much higher than 60, so you cannot use this as a vapor barrier. It can be insulation, but then you have to add up a vapor barrier, which can be a membrane. There are many type of membranes that you can put. In many places, we use poly. Poly has the problem that is really low permeance, so has some people are avoiding using poly because when you have 60, you're allowing some excessive moisture to go through. So if you have an excessive moisture, you might be able to. But guys, this is going to get you more confusing. Let's stick with that. The code requires you 60, and everything has to be below 60 to be considered a vapor barrier. You know the table. Okay, so we're almost at 2. I think we have to wrap up. Thank you guys. This is really intense. I wish you luck on the exam, and I will write down some answers from the list and send you back some clarifications.
Thanks. Thank you, sir. Good luck.
Is he done? I don't know how to read Appendix C.
So I'm being told that
It's here.
Where?
It's in the first book. It's in part 2. I don't know how to read it.
okay, I can stay a little bit until the next one. So I have 3 more questions. You know the table is only building energy efficient homes, optional or a requirement. Well, this is something I'm really not that versed on the application of the National Building Code. So it is the energy efficiency is to be the optional one, and the other one is like the minimum requirement. So the energy efficiency is really for if you want to pursue further energy efficiency. Can the whipping tile network be connected to exterior dry well away from building or subways? Yes, and I noted it's one of the slides. You can connect that, and that would be the best way of building a drainage system. You connect that whipping tile to the exterior dry well. Constructively, and this is something fun that I'm sharing, it's a little more complicated because you have to grade the whipping tile, and you have to also grade to the dry well, so you're going to have a very deep dry well, and you have to be sure that you don't have a water table nearby, and that's something that the code requires you.
No, it tells you 3, like the chart that he had. Go back to the chart.
Where is the zone table? Again, I already answered that, but it's on the Appendix C, Division B,
But how do you...
You see like the degree.
on page.
There, 3,000.
It starts on page C11. Okay. Okay, and the last 2. Is there a minimum? So the question is there a minimum? So, okay, I'm sorry, I'm going to, so for the vapor barrier, no, there's no minimum. And this is where the code, so cannot be more than 60, but it can be 0.005, which is actually poly is 0.005. And the most common use vapor barrier is the poly. Can you please explain vapor permeability and vapor barrier? So vapor permeability is the capacity of the material to allow the vapor to flow, and the code tells you have to have a material that is the vapor permeability of the material cannot be more than 60. So any material that has less than 60 can be used as a vapor barrier. Any material means poly or the plastic that you have, that is 0.005. It can be 1 inch of closed cell spray foam, which is 50, which is below 60. It can be, there are like multiple membranes that you can buy, Blueskin, Intello, Cosala Dorcan, that are low vapor permeance. And in the spec, you have to check that that membrane is below 60. Yeah, the max. That's the last question. Okay, and that's it, guys. I have to go. We have to let the next presenter as well. Thank you very much. I hope this was helpful, and again, good luck in the exam.